The next statement is, as I was saying, Chebychev's inequality, and this inequality is a very fundamental one in probability theory. It says the following. Okay, so it says exactly what we wanted before. So suppose t is a random variable, and suppose theta is some parameter, and suppose you know that the expected value of t minus theta whole squared, that is equal to some gamma. Then it says that for any c more than 0, we have that the probability that t minus theta is more than c times square root gamma is 1 by c squared. Okay, is at most 1 by c squared. Can be much smaller, but it's no larger than 1 by c squared. Okay, so that's what Chebyshev's inequality says. Note that earlier all we did was plug in c equals 10. Right? So we said delta is 10 times root gamma. Okay, so let's see how to prove this thing. So I will prove this in the case of discrete random variables. Okay, so the proof of continuous random variables is almost identical. You have to replace things by integrals, but the idea is roughly the same. Okay, so what is the idea, right? So t is some random variable and theta is some parameter. Okay, so for the case of discrete random variables, let's say that you have, so know that in this case the probability density function just looks like this. So there are some values. Okay, so let's say the values taken by this are a1, a2, a3 up to am, and let's assume that this probabilities are p1, p2 up to pm. Okay, and theta is, let's say, some value. Theta need not be one of the ai's. Theta is some value like this. Now what does it mean that expected value of t minus theta whole squared equals gamma? Right, so what does that mean? So this is equivalent to saying that sum going from 1 through m of pi times ai minus theta whole squared, this is equal to gamma. Okay, because t takes values, so t is in the notation that we used to use before, t is this random variable that is a1 with probability p1, a2 with probability p2, and so on to am with probability pm. Okay, and this is simply saying, so we saw an expression for how you have if you have a function of a random variable. In this case, the random variable is t and the function is t minus theta whole squared. Then the expected value, this is how we write it down. Okay. So this is what we have. Okay. So we know that this fact is true. Okay. So now let us define, let S be the set of all indices I for which the absolute value of t minus theta is more or bigger than or equal to, actually here I could even have written this, so it's bigger than or equal to c root gamma. Okay, so if S is the set of all indices like this, so formally I write S like this, set of all I such that this is ai minus theta. This is that ai minus theta is more than or equal to c root gamma. Okay. So now I can write down this summation. So let's look at what this equality star is saying. So star, I could write it down as sum over I in S of pi ai minus theta whole square plus sum over I naught in S of pi ai minus theta whole square. This we know is equal to gamma. Okay, so this is very simple. So this is just the definition, because this in star the summation went over all indices. I am splitting the indices into those in S and those not in S. Okay, so this fact really holds. And so what this implies is that if I ignore the second term, then the second term is clearly positive because p is positive and this is some square which is always positive. So the first term is always less than or equal to gamma. Okay. So from this we have that sum over I in S pi ai minus theta whole squared, this is less than or equal to gamma. But now what is S, right? So S is defined as all indices I for which ai minus theta is more than c times root gamma. So this, as we saw before, so this is equivalent to saying that ai minus theta whole squared is bigger than or equal to c squared gamma. Okay, so in particular, the left hand side of this last inequality out here, so left hand side of this, so this is bigger than or equal to sum over I in S pi times c squared gamma. Okay, and so we know that sum over I in S p is c squared gamma. This is less than or equal to gamma, right? So therefore, so I will write this a little bit differently. C squared gamma times sum over I in S pi. This is less than or equal to gamma. Okay, just from this inequality. Okay, so we had this thing less than or equal to gamma, and we knew that this quantity is bigger than or equal to this. Therefore, therefore the leftmost term is less than or equal to gamma. Okay, so this is what we have, and now I can cancel out the gamma over here, and now you get sum over I in S of pi. This is less than or equal to 1 by c squared. Okay. So now what is this term? Right, so this term is exactly equal to the probability that t minus theta is less than or equal to c root gamma. And why is that? Because I am summing over all I in S of the probability of I, right? So I in S was exactly all the events that were of interest, right? So this is all the values of t where t minus theta was more than c root gamma. Okay? And what I'm saying is that if you sum the probability values over all the elements in the set, those probabilities add up to at most 1 by c squared. Okay? And this is exactly what we claimed, and this completes the proof. Okay, so the important thing here is observing that this probability of t minus theta more than c root gamma, so that's equal to this quantity. Okay, so this is why I chose to do this proof in the discrete case, because if you are not so if you want to review this equality should be, try to spend time to convince yourself that this equality holds. In the continuous case, it will involve an integral, and then some people might get confused. Okay, so but the proof is basically the same even in the continuous case, right? So that's Chebychev's inequality, and note that once I plug in c equals 10, I exactly get what we have here. Okay, so where did this all come from, right? So let's go back to where this came from. So what we were asking is, suppose you know the mean squared error of some estimator t. Okay, so we know that the mean squared error is gamma, or we know that, let's say, it's smaller than or equal to 1 or something like this. Then we wanted to come up with confidence intervals, right? And I'd like to argue that this is exactly what Chebychev's inequality gives us, right? So there's a, let me write it as a corollary of Chebychev's inequality.